Welcome. Let this be a time for nothing but rest. Let your breath slow, your shoulders soften, and your eyelids grow heavy, with nothing left to do tonight but listen and drift. Tonight we wander gently through one of the oldest wonders the mind has ever held, the size of everything there is. The universe is expanding. In every direction, galaxies are slowly drifting apart, carried outward by the quiet stretching of space itself, a soft and ceaseless growing, larger than any single mind, unfolding everywhere, at every moment. Hubble's law describes a simple relationship between how far away a galaxy lies and how quickly it seems to be moving away from us. The farther the galaxy, the faster its retreat. Astronomer Edwin Hubble noticed this gentle pattern nearly a century ago, watching distant lights recede in every direction. It is as though space itself were a great, slowly inflating fabric, carrying every galaxy a little farther from every other, softly, endlessly, without any galaxy at its center. The cosmic microwave background is the ancient afterglow of the Big Bang, a faint warmth still glowing across the entire sky. It is the oldest light we can ever hope to see, released when the universe first became clear enough for light to travel freely. Wherever a telescope points, this soft glow is there, a gentle, uniform hush, left over from the universe's earliest morning. The universe is approximately 13.8 billion years old. That is a span of time so vast that human history barely registers as a breath within it. Stars have been born and faded many times over across that stretch. Galaxies have gathered and grown, and still, that great age is only the beginning of how far back the story reaches. Everything we know is young compared to the age of the whole. Light from distant galaxies takes billions of years to reach us, arriving tonight as a quiet message sent long before Earth ever existed. Looking upward is, in a real sense, looking backward through time itself. The light entering your eyes tonight left its galaxy before our earliest ancestors ever walked this world. It has traveled alone, through the dark, patiently, for longer than imagining, just to arrive here, now, softly. The observable universe stretches outward about 46.5 billion light-years in every direction around us. This vast sphere is simply the farthest reach of light that has had time to travel to us since the beginning. Beyond its edge, there may be far more universe waiting, unseen, simply because its light has not yet had the time to arrive. Redshift in the light of galaxies tells us that they are moving away from us, stretching their light toward longer, redder wavelengths as they go. It happens much like the falling pitch of a train's whistle as it fades into the distance. Astronomers read this gentle reddening like a quiet signature, a soft clue written across starlight, telling the story of a universe still slowly spreading apart. The Hubble constant measures how quickly the universe is expanding right now, in this present moment. It is usually described as about 70 kilometers per second for every megaparsec of distance, a gentle rate that adds up across the vastness of space. Scientists still refine this number carefully, comparing measurements from many different corners of the cosmos, patiently narrowing in on its true quiet value. General relativity, Einstein's theory of gravity, describes how the universe bends and curves on its grandest scales. In this graceful picture, gravity is not a pull between objects, but the gentle curving of space and time itself around mass and energy. Stars, galaxies, and even the whole universe rest within this quiet, flexible fabric, shaping it softly even as it shapes them in return. Einstein's field equations permit more than one possible shape for the universe's geometry. The very same elegant mathematics can describe a universe that curves back on itself, one that stretches flat forever, or one that opens outward without end. Which shape truly describes our universe is not decided by the equations alone, but by careful, patient measurement of the cosmos itself. Let your shoulders soften now, and let your jaw loosen gently. There is nothing to figure out, nothing to hold on to. Each breath can grow a little slower, a little deeper, like a tide easing back from the shore. Let your thoughts drift without needing to follow any of them. You are simply resting here, safe and unhurried, while the universe continues quietly on, asking nothing of you at all. On the very largest scales, the universe appears remarkably uniform. If you could zoom out far enough, past individual galaxies and even great clusters, the cosmos would look much the same everywhere, like a fine, evenly woven cloth. This smoothness, called homogeneity, only reveals itself across truly enormous distances. Up close, matter clumps and gathers, but stretched wide enough that clumping fades into a gentle, consistent hum. The universe also appears isotropic, meaning it looks the same in every direction we turn our eyes. Whether we gaze north or south, upward or down, the distribution of galaxies and light shows no favored direction at all. It is as though we are floating in the very center of a softly glowing sphere, with no side brighter or busier than any other. This balance feels almost like a quiet, symmetrical breath held evenly on every side. From these two calm observations, scientists have gently proposed something called the cosmological principle. It suggests that no place in the universe is special, that Earth's corner of space holds no more importance than any distant, unseen region. This idea helps cosmologists study the universe as a whole, trusting that the laws and patterns we observe here would look the same from almost anywhere else, however far away. Galaxies rarely drift alone through the darkness. Instead, they gather softly into clusters, sometimes holding thousands of galaxies bound gently together by gravity. These clusters then arrange themselves into even larger structures called superclusters, vast rivers and webs of galaxies stretching across unimaginable distances. Seen from far enough away, this cosmic web resembles delicate lace, its threads glowing faintly, its open spaces quiet and dark. Our own Milky Way is only one gentle light among an estimated 2 trillion galaxies that we can currently observe. Each of those galaxies holds its own quiet multitude of stars, planets, and perhaps stories we will never know. It is humbling and comforting all at once to consider how many other soft spirals and drifting clouds of stars share this same expanding darkness with us tonight. Within all of those galaxies together, scientists estimate there are roughly 10 followed by 23 zero stars shining across the observable universe. It is a number so large that it slips quietly past ordinary imagination, like trying to count grains of sand across every beach on Earth combined. And still, this immense number describes only the portion of the universe we can currently see. Galaxies are not truly swimming through some fixed, unmoving space. Instead, space itself gently stretches, carrying galaxies apart the way raisins in a rising loaf of bread drift farther from one another as the dough expands. The galaxies themselves barely move within their own local surroundings. It is the fabric between them that quietly grows, widening the distances softly over unimaginable stretches of time. Wherever we look, we find no observed center to this vast expansion. Every galaxy appears to be moving away from every other galaxy, evenly, in all directions, no matter where the observer happens to stand. This is much like the surface of a slowly inflating balloon, where every dot drifts farther from every other dot, and no single point can rightly claim to be the middle. The Big Bang, gentle as it may sound now, was not an explosion happening inside some existing empty space. It was the expansion of space itself, unfolding from an extremely small, extremely dense state. There was no outward blast into surrounding emptiness, no center from which matter scattered. Space simply began stretching everywhere at once, quietly carrying the seeds of everything within it. In the tiniest fraction of the first second, scientists believe the universe underwent an extraordinary burst of expansion known as cosmic inflation. In far less time than it takes to blink, space itself stretched by an almost unimaginable factor. This brief, furious growth smoothed out early irregularities and set the stage for the gentle, orderly cosmos we observe today. It is a humble idea explaining an almost unthinkable beginning. For now, let your attention rest, with nothing to hold and nowhere to be. Let your shoulders sink a little further into softness beneath you. Feel your breath slow, arriving and leaving without effort, like tide easing along a quiet shore. There is nothing to solve tonight, nothing to remember, just this slow, unhurried breathing, carrying you gently toward rest. The cosmic microwave background carries a temperature of about 2.725 degrees above absolute zero, and remarkably, this temperature is almost perfectly the same everywhere we look. This faint afterglow bathes the entire sky in a whisper of ancient warmth, barely above the coldest possible cold. Its extraordinary evenness quietly tells us that the early universe, too, was remarkably smooth and uniform. Within that near-perfect smoothness, scientists have found extremely small variations, temperature differences of only a few parts in 100,000. These tiny ripples were like faint seeds scattered across the early universe. Over vast stretches of time, gravity gently drew matter toward these slightly denser patches, slowly gathering gas and dust, until galaxies and clusters of galaxies began to bloom. Long ago, sound waves rippled through the hot, dense plasma of the infant universe, compressing and releasing matter in gentle, rhythmic pulses. These are known as baryon acoustic oscillations, and their faint imprint remains fixed in the arrangement of galaxies today. Like ripples frozen in sand after a wave recedes, these ancient patterns quietly reveal the size and rhythm of the universe's earliest moments. When scientists speak of the universe's large-scale shape, they describe three gentle possibilities: flat, open, or closed. Each describes how space itself curves across the grandest of scales. It is much like comparing a flat tabletop, a saddle that curves outward, and a sphere that curves back upon itself. These three quiet geometries shape how light travels, how parallel lines behave, and how vast the universe might ultimately be. If the universe's geometry is flat, then in the simplest models, space extends forever in every direction, without edge or boundary. Picture an endless tabletop stretching quietly beyond any horizon, never curving back, never closing in on itself. This flatness would mean that parallel lines remain forever parallel, and the vast quiet plane of existence never folds into a repeating shape. A closed geometry, by contrast, describes a universe that curves gently back upon itself, much like the surface of a sphere. In such a universe, space would be finite, though still without any edge to bump against. Traveling far enough in one direction might, in principle, eventually return you to where you began, the way a traveler circling a globe returns quietly to their starting shore. An open geometry describes a universe curving outward like the surface of a saddle, stretching endlessly without ever closing upon itself. This gentle negative curvature would also mean the universe is infinite, though shaped differently from the flat case. In such a universe, parallel lines would slowly drift apart, spreading wider the farther they traveled through the softly warped fabric of space. Using extraordinarily precise measurements, the Planck satellite examined the faint afterglow of the Big Bang and found the universe's geometry to be flat, with an uncertainty of only about 0.4%. This is a remarkably delicate measurement, akin to checking whether an enormous unseen tabletop tilts by the width of a single hair. Within our current reach of instruments, the universe appears strikingly, quietly flat. Nearly 70% of everything in the universe is something we cannot see or touch, called dark energy. Scientists believe this mysterious energy fills the whole of space itself, pressing outward with a steady, invisible hand. It has no known particles, no light, no shadow, and yet its influence shapes the destiny of every galaxy. We name it, we measure its effects, but its true nature remains one of the deepest quiet mysteries in all of science. Roughly 27% of the universe's mass and energy is made of dark matter, another invisible presence woven through the cosmos. It does not shine, and it does not reflect light. Yet, its gravity gently cradles galaxies, holding their swirling stars together. Astronomers infer its presence only through the way it quietly bends light and guides motion. It drifts unseen through every galaxy, a silent companion to the visible stars. For a little while, let go of every thought you've been carrying. Let your shoulders soften into the surface beneath you, and let your breath grow long and unhurried. There is nothing to solve tonight, nothing to remember, nothing to hold. Just the slow rise and fall of breathing, gentle as tide, gentle as rest. Let your mind drift, soft and weightless, like a small light floating quietly through a warm and endless dark. Everything we can see, touch and measure directly, all the stars, planets, and glowing clouds of gas, makes up only about 5% of the universe. The rest remains hidden in dark matter and dark energy, unseen companions to the visible world. It is a humbling thought that the familiar universe of light and stone is only a thin, glowing surface atop something far vaster and stranger, still waiting to be understood. The universe is not only expanding, it is expanding faster with each passing moment. This gentle acceleration, discovered through careful observation, surprised scientists who once expected gravity to slow everything down. Instead, dark energy seems to be pressing space outward with ever-growing strength. Distant galaxies are drifting apart a little more quickly with every billion years, carried on a widening tide that never seems to ease. The simplest explanation scientists have found for this accelerating expansion is something called the cosmological constant. It describes a steady, unchanging energy filling every corner of empty space, quietly pushing outward with the same gentle strength everywhere and always. Einstein once considered a version of this idea, then set it aside, only for later observations to bring it softly back into view, resting quietly at the heart of modern cosmology. To measure how the universe has expanded through time, astronomers study a special kind of exploding star called a type Ia supernova. These distant stellar flares burn with a reliably similar brightness, making them useful as cosmic measuring posts. By comparing how bright they appear to how bright they should be, scientists can trace the universe's expansion across billions of years, like reading gentle notes left behind in ancient starlight. What becomes of the universe in the farthest future depends on how dark energy behaves as time continues onward. If it remains steady, the galaxies will simply drift ever further apart, fading gently into darkness. But if its strength should shift, the story could unfold quite differently. Scientists continue watching patiently, gathering starlight like clues, unhurried in their search for what lies at the end of time. There is a boundary to what we can ever see, a soft edge shaped simply by the age of light itself. Beyond it, space may continue, but no signal from those distant reaches has ever had time to reach us. It is not a wall, not an ending, only the quiet limit of visibility itself, the furthest whisper of light our eyes have yet received from across the universe. The furthest edge of what we can presently observe is called the particle horizon, marking the outer reach of visible light's long journey. It represents the greatest distance light has had time to travel since the universe's earliest moments. Beyond this soft boundary, the universe likely continues, quietly unseen, simply because its light has not yet arrived. It is less a wall than a patient unfolding, still in progress even now. There exists a boundary called the cosmic event horizon, marking the furthest place we could ever reach or influence, even with light itself. Beyond this gentle threshold, space is expanding so quickly that nothing sent from Earth, not even a beam of light, could ever arrive there. It is not a wall but a horizon of possibility, a soft limit on our future reach, however patiently we might try to cross it. Light from regions farther than about 46.5 billion light-years away has simply not had time to reach us yet. This unimaginable distance is not the edge of the universe, but the reach of our patience, the furthest whisper light has managed since the beginning. Somewhere beyond it, stars may be shining right now, their glow still traveling quietly toward a future Earth that has not yet arrived to receive it. The true universe, scientists gently suspect, may reach far beyond the portion we are able to observe. What we see is only a modest window, framed by the age of light itself, while the full expanse could stretch on in ways we may never fully witness. It is a humble thought, holding within it a quiet kind of wonder that so much may exist beyond our softest reach. For a little while now, let your thoughts simply drift, unattached to any question or answer. There is nothing to solve here, nothing to hold on to. Let your breath slow, soft and even, like tide gently receding from shore. Feel your body grow heavy, sinking into rest, as if the whole universe were holding you gently, asking nothing of you at all. Just drift, slow and unhurried, toward sleep. Even a universe measured as flat could still, in principle, be finite if its underlying shape carries an unusual twist. Flatness describes how space curves locally, but says nothing about how that space might connect with itself on the largest scales. It is a gentle reminder that appearances, even in cosmic geometry, do not always tell the whole quiet story. Imagine a universe shaped like a torus, a soft cosmic donut, curving gently back upon itself in every direction. Such a shape could appear perfectly flat to anyone measuring nearby, and yet still be entirely finite in its total size. Traveling far enough in a straight line, one might simply arrive back where they started, having circled the whole of existence without ever meeting an edge. No measurement of local curvature alone can ever reveal the universe's true topology, its overall shape and connectedness. Two universes could share the exact same gentle flatness nearby, while one stretches on forever and the other loops quietly back upon itself. Understanding the larger shape requires clues that reach far beyond what any single point in space can offer. Two remarkable missions, named WMAP and Planck, spent years mapping the cosmic microwave background with extraordinary precision. Each captured the faint afterglow of the early universe in ever finer detail, painting a soft mosaic of temperature differences across the entire sky. Their careful work has given scientists one of the most precise portraits of the infant cosmos ever gathered. Despite the most careful searching, no repeating patterns have ever been found within the cosmic microwave background that might suggest a small, tightly looping universe. If space folded back on itself soon enough, matching patterns of warmth and coolness might appear scattered across the sky. Their quiet absence tells us something gentle yet significant, that if the universe is finite, it must be remarkably vast. Because no matching patterns have been found, scientists can gently estimate a lower bound on how large any finite universe would have to be. It sets a soft threshold, a size beneath which we can be fairly confident the universe does not fold. Beyond that threshold, the question remains tenderly open, leaving room for wonder that stretches far past what any telescope has yet confirmed. Scientists have developed a gentle technique known as the circles in the sky method, searching for matched patterns from a finite universe wrapping quietly around itself. If space folded back on itself, light could travel all the way around and return, painting faint matching circles of temperature onto opposite patches of the sky. Researchers have scanned these patterns with patient, careful eyes. It is a soft kind of search, listening for an echo that light itself might carry. After all this careful searching, no matched circles have ever been found, suggesting that any finite universe must be extremely large. The absence is not a disappointment, but a quiet clue, narrowing what shape our cosmos might hold. It tells us gently that if space does curve back upon itself, it does so on a scale far grander than anything nearby. The silence itself becomes a kind of soft evidence. Because of this, the minimum possible size of a closed universe now exceeds the observable horizon itself. Whatever curve might exist, it stretches beyond the very edge of what light has had time to show us. This means that even our vast observable universe, 46.5 billion light-years across, could sit like a small pebble within some far larger, gently curving hole. The true scale, if it curves at all, dwarfs anything we can currently trace. Today, astronomers measure the universe's expansion at roughly 70 kilometers per second for every megaparsec of distance. This means that for every added stretch of about 3 million light-years, galaxies appear to recede a little faster, carried outward by the gentle stretching of space itself. It is a steady, calm rhythm, one that has been measured again and again with growing precision. This number quietly anchors much of what we understand about the universe's size and age. For a little while, let your thoughts loosen their grip entirely. There is nowhere to be, nothing to solve, no thread left to follow. Feel your breath settle into its own slow rhythm, each inhale a little softer than the last. Let your shoulders sink, your jaw ease, your hands rest heavy and still. You can simply drift now, held gently, needing nothing at all. A set of equations known as the Friedmann equations mathematically describe how the universe expands over time. Derived from the deeper framework of general relativity, they trace how the balance of matter, energy, and geometry shapes the unfolding of cosmic space. These quiet lines of mathematics let scientists calculate how fast the universe grew in its past and how it might continue to grow into its future. They form a kind of gentle blueprint for cosmic history. There exists a precise density, called the critical density, at which the universe's geometry would be exactly flat. Above this density, space would curve inward upon itself. Below it, space would curve gently outward, stretching endlessly. This threshold acts like a delicate balancing point, a value so exact that even slight shifts above or below it lead to entirely different cosmic shapes. To describe this balance, scientists use a value called omega, the density parameter, which compares the universe's actual density to that critical threshold. An omega of exactly 1 describes a flat universe. Values above or below that gentle line describe a universe that closes in on itself or stretches open forever. Current measurements place omega remarkably close to that perfect balance, within a hair's width of flatness. In 1922, a mathematician named Alexander Friedmann first derived equations describing a universe that could expand or contract over time. Working from Einstein's own equations, he found solutions that Einstein himself had not expected, solutions describing a cosmos in motion rather than a static, unchanging one. His quiet mathematical insight arrived years before observational evidence would confirm that the universe was indeed expanding. Just a few years later, in 1927, a physicist and priest named Georges Lemaitre independently proposed his own model of an expanding universe. His work, developed without knowledge of Friedmann's earlier findings, would later become closely linked to the very idea of the Big Bang. Two minds, working separately, arrived at the same gentle truth, that the universe is not still, but quietly, continuously growing. The most recent measurements slightly favor a flat universe. yet they do not fully rule out a gentle curvature. The data leans, ever so faintly, toward that perfect balance point. But within the soft edges of uncertainty, a slightly closed or slightly open universe still remains possible. Nature may be flatter than flat, or it may curve so gently that no instrument yet built could ever notice the difference. This small margin of uncertainty in curvature leaves a quiet door open for a closed universe. Even the most precise satellites cannot yet declare, with total certainty, that space stretches on forever. Somewhere within that narrow sliver of possibility, a finite cosmos curving gently back upon itself could still exist. Science holds this option softly, without insisting on an answer. In earlier decades, cosmologists imagined that a closed universe, one curving back on itself, would eventually stop expanding and slowly collapse inward. This model painted a graceful arc, expansion rising like a breath, then falling gently back toward a single point. It was a tidy, symmetrical vision, matter and gravity locked in a slow, inevitable embrace, drawing the cosmos home again. Modern observations, however, have gently set that recollapsing model aside. The discovery that cosmic expansion is accelerating, rather than slowing, does not fit comfortably with a universe destined to fall back on itself. Dark energy appears to push outward, not inward, suggesting that even a closed universe, if it exists, might stretch onward rather than return. The old, tidy picture has softened into something more open-ended. To explain the universe's shape without demanding an infinite expanse, some researchers have proposed unusual finite topologies, among them a shape called the Poincare dodecahedral space. Picture a 12-sided form, its faces mysteriously connected so that traveling out one side returns you through another. It is a strange and elegant idea, a finite cosmos folded upon itself in a way too subtle for ordinary geometry to capture. For now, let your thoughts loosen, like a hand slowly opening. There is nothing to solve, nothing to hold on to. Let your breath grow slower, longer, easier. Feel your body settle a little deeper into softness. Nowhere to be, nothing to do. Only this quiet moment, drifting gently, gently downward, toward rest. A universe can be finite without ever having an edge, if its space is what mathematicians call multiply connected. In such a universe, traveling far enough in one direction might simply bring you back to where you began, not because you struck a wall, but because space itself loops gently around. There is no boundary to find, no edge to touch, only a quiet, curling return. In such a looping universe, an observer might, in principle, see the very same galaxy appear in more than one direction of the sky. Light from that galaxy could travel around the looping space by different paths, arriving from opposite sides like echoes of a single sound. The sky itself might quietly repeat, showing the same distant light twice, without the observer ever realizing it at first glance. An infinite universe, by its very definition, has neither an edge to reach nor a center to stand at. Every point within it would feel just as central, or just as uncentral, as any other. There would be no wall to travel toward, no middle to search for. Space would simply continue, in every direction, without ever needing to end. Determining the true shape of the universe would require observing scales far larger than anything currently visible to us. Since light beyond the observable horizon has not yet had time to reach Earth, any pattern revealing the cosmos as finite or infinite may lie forever just out of reach. We are left gazing at a single, gentle slice of a much larger, unseen whole. Cosmic inflation stretched space so violently in its earliest moments that any original curvature was smoothed almost perfectly flat. Imagine a wrinkled sheet pulled taut until every fold disappears from view. Even if the universe once curved sharply, That curvature would now be spread so thin across such vast distances that our observable patch appears flat, no matter its true underlying shape. Inflation theory gently suggests that separate pocket universes could form, each with its own distinct geometry. As different regions of an inflating space stopped expanding at different moments, they may have settled into their own shapes, some flat, some curved, some closed. Each pocket would feel like its own complete universe, unaware of any other, sealed quietly within its own portion of an ever-stretching whole. Eternal inflation proposes that this stretching may never fully stop everywhere at once. In certain models, while some regions settle and slow, others continue expanding indefinitely, forever bubbling onward. It is a little like a pot that never quite finishes boiling in every corner, with fresh pockets of rapid expansion continuing to arise, even as others quiet down. Within this endless process, bubble universes could form again and again without any final limit. Each bubble might emerge from the restless energy of the inflating background, drifting outward like a slow, silent bloom. Some physicists picture this as an infinite froth of universes, each one separate, each one quietly its own, forming continuously through unfathomable stretches of time. Each of these bubble universes might carry its own physical constants, its own subtle laws, the strength of gravity, the mass of particles. Even the number of dimensions could differ from one bubble to the next. Our own universe, with its familiar starlight and steady gravity, might simply be one gentle variation among countless others, each following its own quiet internal rules. This idea widens gently into the broader concept of a multiverse, a vast collection of possible universes beyond our own. It is less a single cosmos than an unimaginable garden of cosmoses, each blooming according to its own conditions. Our entire observable universe would be only one blossom among an uncounted silent field. For now, let your thoughts loosen, drifting like light with nowhere urgent to arrive. There is nothing to solve here, nothing to hold on to. Let your shoulders soften into the bed beneath you. Let your breath slow into its own easy rhythm. You need only rest, carried gently by the quiet dark, with nowhere to be but here. The multiverse hypothesis, for all its quiet elegance, remains scientifically unproven and largely untestable. We have no telescope capable of peering into another bubble universe, no signal that could confirm its presence. It remains a graceful mathematical possibility, one that many physicists find compelling, yet one that still waits patiently outside the reach of direct evidence. If space truly stretches on without end, the arrangement of matter within it might eventually repeat itself, unimaginably far away. Somewhere beyond any distance we could ever traverse, similar patterns of galaxies, similar swirls of stars, might quietly arise again by simple chance. It would not be an echo of our sky, but simply another roll of the same vast dice. This idea leans on a simple truth, that space without end, combined with only a finite number of ways particles can arrange themselves, implies patterns must eventually recur. With endless room but limited possible configurations, certain arrangements would, in principle, appear again and again across the vastness. It is a gentle consequence of probability stretched across infinity, nothing more mysterious than numbers finding room to repeat. This reasoning leads gently toward the idea of duplicate Hubble volumes scattered elsewhere in space. If patterns of matter can recur across an endless expanse, then whole regions resembling our own might exist, far beyond any horizon we could reach. It is not a claim of certainty, only a soft mathematical possibility, following naturally from infinity and probability, held side by side. A Hubble volume is simply the region of the universe we can currently observe from Earth. It is the sphere of space from which light has had time to reach us since the universe began. Beyond its soft edge, space continues, unseen and untouched by our instruments. Our Hubble volume is not a boundary of reality, only the limit of what our eyes, however powerful, can presently gather. An infinite universe could, in principle, hold countless identical copies of Earth. Somewhere, in that boundless expanse, if the reasoning holds, another blue world might turn quietly beneath another sun. Every mountain, every shoreline, every small detail might exist again, simply through the endless shuffling of matter across infinite space. It is a strange and tender thought offered softly by mathematics. This idea of countless Earths is a probabilistic consequence, not something anyone has observed or confirmed. No telescope has ever glimpsed a second Earth, near or far. It arises purely from following mathematics to its natural end, allowing numbers to wander freely across an assumed infinity. The universe may or may not honor this quiet suggestion. For now, it remains a gentle thought experiment. The concept of cosmic duplicates arises from probability theory applied to infinite space. Just as shuffling a deck of cards long enough may eventually repeat a sequence, an infinite universe with finite particle arrangements may repeat certain patterns endlessly. It is simple logic borrowed from mathematics, applied gently to the largest canvas imaginable. Nothing mystical, only numbers finding room to echo themselves. The distances between any such duplicate regions would be unimaginably vast, far beyond anything we could ever traverse or even meaningfully picture. We are not speaking of nearby stars or distant galaxies, but of spans so enormous that light itself would need far longer than the universe's entire age to cross them. Such distances exist mostly as numbers on a page, gentle abstractions stretching past all human scale. This entire idea rests on one unproven assumption, that space itself truly extends without end. If space is instead finite, curling gently back on itself, this reasoning quietly falls away. Everything about duplicate worlds and repeating patterns depends on that single, still unanswered question. Scientists hold this possibility softly, aware that its foundation remains, for now, beyond our reach to confirm. For a little while, let your mind simply rest without reaching for any answer. There is nothing you need to work out, nothing you need to hold in place. Let your breathing settle into something slow and even, like a tide easing toward stillness. Let your body grow heavy, sinking softly into the warmth beneath you, safe and unhurried in this quiet, drifting dark. Mathematicians draw a careful distinction between potential infinity and actual infinity. Potential infinity describes something that can always continue further, like counting numbers one after another without ever finishing. Actual infinity, by contrast, describes something already complete, an endless whole held all at once. This gentle distinction shapes how thinkers have approached the idea of infinity for centuries. Actual infinity refers to a completed, existing infinite set, whole and finished, rather than endlessly unfolding. It is the idea of infinity, not as a process reaching forward, but as a totality already there, fully formed. Mathematicians can work with such infinite sets with precision, even though nothing in our daily experience quite resembles them. It remains a concept easier to hold in thought than to picture in the world. Potential infinity describes an unbounded process, one that never finishes, but is always finite at any single moment we examine it. Imagine counting upward, 1, 2, 3, forever able to continue, yet at every pause you have only reached some particular finite number. The infinity here lives in the possibility of continuing, not in any completed total. It is a gentle, forward-leaning kind of endlessness, always becoming, never quite arrived. Ancient Greek philosophers spent long, thoughtful hours debating whether true infinity could exist within the natural world. Some imagined the cosmos as boundless, extending without limit in every direction. Others felt certain that nature preferred wholeness, measured shapes, and definite edges. Their conversations, held under open skies over 2,000 years ago, still echo quietly through the questions we ask about the universe tonight. Aristotle, one of those ancient thinkers, ultimately rejected the idea of actual infinities existing in the physical world. He accepted potential infinity, the idea of endless continuation, but felt a completed infinite whole could never truly exist among real things. In his view, nature always presented itself in finite, bounded form. His reasoning shaped Western thought about infinity for well over 1,000 years afterward. Many centuries later, the mathematician Georg Cantor formalized the idea that infinity itself could come in different sizes. Working in the 1870s, he showed that some infinite collections are, in a precise mathematical sense, larger than others. This was a striking, almost dreamlike revelation that endlessness was not a single uniform idea, but a whole landscape of distinct infinities. His work quietly reshaped the very foundations of mathematics. Cantor's set theory carefully distinguishes between countable and uncountable infinities, two very different kinds of endlessness. Countable infinities, like the whole numbers, can be listed one after another, even if the listing never finishes. Uncountable infinities, like the points along a single line, are so dense and continuous that no such listing could ever capture them all. Both are boundless, yet one is, in a gentle mathematical sense, deeper than the other. Whether physical space itself can be actually infinite remains a living, ongoing debate among physicists today. It is not a settled question, but one still turned over carefully in papers, conferences, and quiet late-night conversations. Some evidence leans one direction, some leans another, and much still depends on measurements not yet possible. The universe, in this sense, keeps a soft and patient silence about its own true extent. Some physicists argue that true, actual infinities simply cannot exist anywhere within the physical universe. They suggest that anything we measure, count, or observe must ultimately be finite, even if extraordinarily large. In their view, infinity may be a wonderful mathematical tool, but perhaps not something nature itself ever fully embodies. This remains a thoughtful, reasoned position, held with quiet conviction rather than certainty. Other physicists argue, just as thoughtfully, that mathematics naturally permits, even gently invites, the possibility of a truly infinite universe. They point out that our best equations for cosmic geometry allow flat or open space to extend forever without contradiction. For them, infinity is not a strange exception, but a smooth, natural outcome of the mathematics we already trust. Both views remain respected, sitting peacefully side by side in modern cosmology. For now, let these thoughts of endlessness soften and drift away, with nothing left to hold on to. There is no need to decide anything, no need to reach any conclusion tonight. Let your shoulders loosen, let your jaw unclench, let your breath grow slow and unhurried. Feel yourself sinking a little deeper into softness, carried gently toward rest, held safely in this quiet, dim, unhurried dark. Theories of quantum gravity may one day change how we understand space-time itself at its very smallest scales. These theories try to gently merge two great pillars of physics, quantum mechanics and general relativity, which have never quite fit together smoothly. At the tiniest imaginable distances, space may behave in ways nothing in our ordinary experience resembles. Scientists continue this patient work, hoping to understand what space truly is, down at its deepest foundation. The smallest length that physics still considers meaningful is called the Planck length. It measures roughly 10 to the negative 35th power of a meter, a distance so small that comparing it to an atom is a little like comparing an atom to an entire galaxy. Below this scale, our familiar laws of physics quietly lose their footing. Scientists believe something new, still undiscovered, must gently take over at this delicate threshold of measurement. At this smallest of scales, space itself may not be smoothly continuous. Instead of flowing without interruption, like a calm sheet of glass, space might be built from tiny, indivisible pieces. Imagine looking closer and closer at what seems an endless silky fabric, only to find, at last, a delicate grain. Physicists gently suspect the universe's smoothness may simply be an illusion created by the ordinary larger scale at which we live. Loop quantum gravity offers one gentle answer, suggesting space is woven from tiny quantized units. In this view, space is not an empty stage, but something like a fine, glowing net made of interlocking loops far too small to see. Area and volume themselves come in discrete, countable steps rather than flowing values without limit. It is as though the universe has its own smallest possible brushstroke, from which everything larger is patiently painted. If space truly is discrete, the word infinite might take on a slightly different meaning. Rather than a smooth, unbroken continuum stretching forever, infinity might instead mean an endless number of tiny, separate units, each one finite and countable. It would be a little like an endless mosaic, built from countless small tiles, rather than one seamless painted sky. The vastness would remain, only its texture would be granular rather than smooth. String theory allows for a landscape of an almost unimaginable number of possible vacuum states. This number is often written as 10 multiplied by itself 500 times, a figure so large it dwarfs the count of atoms in our entire observable universe. Each vacuum state could correspond to a different way for space, particles, and forces to settle and exist. Physicists picture this landscape almost like an endless mountain range of valleys, each cradling a different possible universe. This string landscape could, in principle, give rise to an infinite variety of distinct universes. Each valley in that vast theoretical terrain might hold a universe with its own laws, particles, even its own version of space and time. Some might resemble our own gently familiar cosmos. Others might be built from constants entirely foreign to us. It is a quiet, staggering thought that our universe's recipe might be only one page from an endless book. The idea of a multiverse arises independently from both inflation theory and string theory, two very different lines of reasoning, one about the early universe's rapid stretching, the other about the deep architecture of matter and energy. Both quietly point toward the same gentle possibility. When separate paths of thought arrive at a similar idea, scientists take note, even while remaining carefully cautious. Neither theory proves a multiverse exists, but together they make the notion feel less like fantasy. Some cosmological models propose a cyclic universe, with repeated big bangs and big crunches. In this gentle rhythmic vision, the universe expands outward for a long age, then slows, gathers, and collapses inward, only to bounce and begin expanding once again. Like breath flowing in and out, or tides rising and receding, existence itself might repeat in unending cycles, each one stretching across ages beyond ordinary imagining. Conformal cyclic cosmology proposes that the universe repeats through a series of successive aeons. In this elegant idea, each vast aeon ends not in violent destruction, but in a smooth, graceful transition, its stretched, thinning space quietly reshaping itself into the birth of the next aeon's Big Bang. Time seems to fold gently onward, aeon after aeon, without any true beginning or end in this repeating chain. Let all of this drift now, gently, like mist dissolving before morning light. There is nothing here to solve, nothing to hold on to, nothing waiting to be understood tonight. Let your breathing settle into its own slow, natural rhythm, each exhale a little longer and softer than the last. Feel the weight of your body sinking comfortably into the surface beneath you, supported completely, resting easily in this warm, unhurried dark. The physicist Roger Penrose proposed this vision, calling it conformal cyclic cosmology. He imagined that the vast emptiness at the end of one aeon might not be an ending at all, but a threshold. Penrose suggested that as the universe grows old, thin, and cold, it could quietly become the fertile ground for a new beginning, as though the cosmos exhales one age and inhales the next without ever truly resting. In cyclic models, such as this one, each aeon could be finite, even while the full history of everything remains infinite in time. Picture a single page in an endless book, complete in itself, yet followed always by another page and another, without any final page ever arriving. Finiteness within, infinity throughout, held together in one quiet, continuous unfolding. In Penrose's model, the end of one aeon flows smoothly into the Big Bang of the next through what is called a conformal rescaling of spacetime. In simple terms, the largest and smallest scales of existence become mathematically interchangeable, so that an unimaginably vast, cold universe can be gently reinterpreted as an unimaginably small, hot one. Nothing breaks or tears. Space merely changes its clothing, and a new beginning quietly appears. Long before these cyclic ideas, another theory once proposed something different, an eternal, unchanging universe with no beginning at all. This was called the steady-state theory, and for a time it offered a peaceful alternative to a universe that started explosively. In this view, the cosmos had always looked essentially the same, matter quietly forming to fill the gaps left by expansion, an unbroken sameness stretching backward and forward forever. This steady-state theory was gently set aside after the discovery of the cosmic microwave background in 1965. That faint glow, discovered almost by accident, carried within it the unmistakable signature of a hot, dense beginning, something a truly unchanging universe could never produce. The evidence was quiet, but unambiguous, and it settled a long, thoughtful debate among careful observers. After this discovery, the Big Bang model became the dominant understanding of our universe's origin. It offered something the steady-state theory could not, a clear explanation for that faint afterglow still detectable in every direction. Since then, decades of careful observation have only strengthened this picture, layer upon layer of evidence settling gently into place, like sediment forming solid ground beneath a quiet river. And yet some theoretical models still gently suggest that the universe's inflationary past may have no true beginning at all. In certain mathematical pictures, inflation could stretch backward through time indefinitely, an unbroken chain with no first link. It is a subtle, delicate idea resting at the edge of what equations can comfortably describe, inviting quiet curiosity rather than firm conclusion. But a mathematical result known as the Borde-Guth-Vilenkin theorem suggests otherwise, proposing that any universe which is, on average, expanding must have had a beginning. Three physicists working together found that this conclusion held true across a remarkably wide range of possible cosmic histories. It gently closed a door that many had hoped might stay open, offering instead a quiet, firm boundary at the edge of time. This theorem implies that eternal inflation, however endlessly it continues into the future, cannot stretch infinitely into the past. Somewhere behind us in the deep architecture of time, there must have been a starting point, even if inflation itself continues without end going forward. It is a strange asymmetry, an arrow pointing only one direction, gently anchoring our universe's story to a definite origin. From these ideas, some theorists have proposed something even larger, what they gently call a multiverse of multiverses, generating endlessly. In this vast conception, not only do bubble universes form within inflation, but entire multiverses might themselves arise and multiply, nested one within another, like patterns folding endlessly inward and outward. It is a dizzying, tender thought, offered softly without certainty, as one more way of imagining how very much may lie beyond our reach. Let your shoulders soften now, sinking a little deeper into whatever is holding you. There is nowhere else to be, nothing left to solve tonight. Let your breath grow long and unhurried, each exhale a little slower than the one before. Thoughts may still drift through, but you don't need to follow them anywhere. Just let them pass, like distant clouds crossing a quiet sky, while your body grows heavier, softer, more at ease. Some alternative models propose something called a big bounce, gently replacing the idea of an initial singularity. In these pictures, our universe did not spring from an infinitely dense point, but instead emerged from the collapse of something that came before. A previous universe, in this tender vision, might have contracted down to an extremely small state, then rebounded outward into the expansion we now observe. It offers a softer beginning, one without a sharp, singular edge. Loop quantum cosmology, a theory blending quantum mechanics with the geometry of spacetime, suggests such a bounce could replace the Big Bang singularity entirely. In this framework, space itself becomes granular at the smallest scales, resisting infinite compression. Rather than collapsing into a point of infinite density, the universe would reach a natural, quiet limit, then gently spring outward again. It is a delicate mathematical vision, offering smoothness where classical equations once broke down. What existed, if anything, before the Big Bang remains completely unknown to us. Our equations, our observations, even our language falter at this threshold. Scientists hold many gentle possibilities, but none can yet be confirmed. It is one of the deepest, most honest mysteries in all of cosmology, held not with anxiety, but with quiet, patient curiosity about what lies beyond our current reach. Some physicists speculate that tiny quantum fluctuations, arising within a pre-existing vacuum, could have gently triggered the Big Bang itself. In this view, empty space is never truly empty, but simmers with faint fleeting energy. A small fluctuation under just the right conditions might have grown into the vast expansion we now call our universe. It is a tender thought, suggesting our entire cosmos could have blossomed from something impossibly small and quiet. Time itself may have begun at the Big Bang, which would make the very idea of before meaningless. If time did not exist prior to that moment, there was no earlier interval in which anything could have happened. This is a gentle but profound shift in thinking, inviting us to release the assumption that every beginning needs something preceding it. Some mysteries, it seems, dissolve the very questions we ask of them. A few exotic theoretical models even propose multiple dimensions of time, rather than the single flowing dimension we experience. In these speculative frameworks, time might have more than one direction in which it can move, layered in ways ordinary experience cannot easily capture. Such ideas remain far from confirmed, existing mostly as mathematical curiosities. Still, they gently expand our sense of just how strange the deep structure of reality might be. Brain cosmology suggests that our entire universe might exist upon a higher dimensional membrane, often called a brain, floating within a larger space. In this picture, everything we know, every star and galaxy, would be confined to this vast surface, like images resting upon the skin of a much larger, unseen structure. Other brains might drift nearby, in dimensions we cannot directly perceive. It is a strange, spacious idea, offered with appropriate humility. In certain ekpyrotic models, the gentle collision of two such brains could theoretically trigger cyclic Big Bangs, again and again, As these membranes drift together across some higher dimensional space, their meeting might release a vast surge of energy, sparking a new expansion much like our own. Afterward, they may drift apart once more, only to return again in some distant future. It is a slow, rhythmic vision of cosmic renewal. This ekpyrotic universe model was proposed as a gentle alternative to standard cosmic inflation, offering a different way to explain our universe's early smoothness and structure. Rather than a sudden burst of expansion, it imagines a slow, patient collision between brains as the true origin of our cosmic history. It remains one among several thoughtful possibilities, quietly coexisting alongside inflation in the wider landscape of theoretical cosmology. String theory gently predicts that our universe may hold extra spatial dimensions, curled up so tightly that they remain hidden from ordinary experience. These additional dimensions, if they exist, would be woven into the very fabric of space itself, far too small for any instrument to have yet revealed them. For now, they remain a beautiful mathematical possibility, unconfirmed by direct observation. Scientists hold this idea with patient curiosity rather than certainty. For now, let your body soften completely into the surface beneath you. Let your breathing slow, each inhale easy, each exhale a little longer and looser than the last. There is nowhere to be and nothing to solve. Simply rest here, drifting gently, as thought grows quiet and heavy, like a candle flame slowly settling into stillness. The Large Hadron Collider, one of humanity's most powerful instruments, has searched carefully for evidence of these extra dimensions, without success so far. Scientists hope that tiny, high-energy collisions might reveal signs of hidden spatial folds. Nothing conclusive has appeared yet, though the search continues patiently. Each null result quietly refines what we understand, or do not yet understand, about the deepest architecture of space. The holographic principle offers a striking idea that all the information within a region of space might be fully encoded upon a lower dimensional boundary surrounding it, much like a hologram stores a three-dimensional image upon a flat surface. Our entire three-dimensional universe might, in some deep sense, be a projection. It is a strange and elegant thought, suggesting that depth itself could be a kind of illusion arising from something simpler. This holographic principle raises deep, quiet questions about the fundamental nature of space itself. If information truly lives upon a boundary, then the space we experience so vividly might be something more like an emergent appearance than a basic ingredient of reality. Physicists continue to explore what this could mean, treating the idea with both wonder and careful mathematical rigor. Some physicists have speculated, quietly and thoughtfully, that our universe could be some form of simulation, an idea that remains currently unfalsifiable. There is no experiment yet devised that could confirm or deny it. It exists mostly as a philosophical curiosity, a gentle invitation to wonder about the nature of reality rather than a claim supported by evidence. The philosopher Nick Bostrom formalized this simulation argument in an influential paper written in 2003. He reasoned carefully about the probabilities involved, exploring what it might mean for advanced civilizations to create simulated realities. His work remains a thoughtful piece of philosophical reasoning, discussed and debated, rather than a settled scientific conclusion. Quantum entanglement reveals a deep and delicate kind of connection across space-time, one that continues to astonish physicists. Two entangled particles can seem linked in their behavior, no matter how far apart they travel, as though sharing an invisible thread that space itself does not sever. This non-local relationship does not violate the deeper laws of physics, yet it quietly challenges our ordinary sense of separateness and distance. Some theorists go further, suggesting that quantum entanglement might be linked to the very emergence of space-time itself, In this view, the smooth fabric of space we experience could arise from countless underlying threads of entanglement, woven together at a much deeper level. It is a speculative and elegant idea, hinting that geometry itself might grow out of quantum connection. The idea known as air equals epper proposes a striking relationship between wormholes and quantum entanglement. It suggests that two entangled particles might, in some deep mathematical sense, be connected by a tiny wormhole linking their locations in spacetime. This elegant conjecture bridges two seemingly separate mysteries, quietly hinting that connection and geometry may be more intertwined than we ever imagined. Wormholes remain purely theoretical shortcuts through spacetime, imagined but never observed. Mathematics permits their existence within the equations of general relativity, curling two distant points together through a hidden passage. No telescope has ever glimpsed one, and no evidence confirms they truly exist beyond these graceful equations. For now, they remain a beautiful possibility drawn only in the quiet language of theory. If the universe is truly infinite, its total mass and energy would also be infinite. Every star, every cloud of gas, every unseen particle would add up without ever reaching a final sum. This is not a flaw in the idea, simply a natural consequence of endlessness itself. It is a thought so vast that the mind can only hold it loosely, like starlight cupped gently in open hands. Let your shoulders soften now, and let your breath slow a little further. There is nothing to solve here, nothing to hold on to, just the gentle weight of your body resting, and the quiet dark settling around you like a blanket. Let your thoughts drift loosely, like faint clouds moving across a still night sky, going nowhere in particular. Infinite total energy poses conceptual challenges for the standard equations physicists use to describe the cosmos. Many of these equations were built with finite quantities in mind, and infinity can cause them to behave strangely or lose their usual meaning. This does not mean the universe is broken, only that our tools sometimes strain at its edges. Scientists have learned to work carefully around these delicate limits. Cosmologists typically use energy density rather than total energy to avoid this very problem. Density describes how much energy fills a given space, a number that stays finite and measurable even if space itself stretches on forever. This gentle shift in perspective allows the mathematics to remain steady and useful. It is a quiet reminder that sometimes changing how we look at a question brings a calmer kind of clarity. Whether infinities in physics represent something truly real or simply artifacts of our mathematics remains a subject of gentle debate. Some scientists believe infinity is woven into the actual fabric of nature. Others suspect it is a sign that our equations have reached the limits of their usefulness. Both views are held with humility, since no one yet holds the final answer. Renormalization techniques in quantum field theory manage other kinds of infinities that once seemed impossible to tame. Physicists developed careful mathematical methods to subtract away infinite terms, leaving behind finite, meaningful predictions that match real experiments beautifully. It was once considered a strange trick, yet it has proven remarkably reliable. This quiet success gives scientists hope that other infinities might someday be understood just as gracefully. Black hole singularities present infinities that current physics cannot fully resolve. At the very center of a black hole, according to general relativity, density and gravity seem to become infinite, a point where the equations simply stop making sense. Scientists suspect this points to missing knowledge, rather than a truly infinite reality. It remains one of the most profound puzzles in all of cosmology. Many physicists believe singularities signal a breakdown of general relativity itself, rather than describing something physically real. In their view, the theory simply was not built to describe conditions of such extreme density and curvature. Something deeper and more complete is likely needed to describe what truly happens there. This gentle suspicion guides much of modern theoretical research. A future theory of quantum gravity might ultimately resolve these lingering infinities, smoothing over the sharp edges where our current physics falls short. Such a theory would gently merge the vast curved world of gravity with the delicate probabilistic world of quantum mechanics. Many researchers spend their careers quietly searching for it. It remains one of physics' most patient and hopeful pursuits. String theory and loop quantum gravity stand today as two leading candidate paths toward a deeper theory of gravity. Each imagines the fabric of reality in a wholly different way, one weaving tiny vibrating strands, the other suggesting space itself is built from delicate, discrete loops. Both attempt to gently reconcile the smooth curves of gravity with the flickering probabilities of the quantum world. Neither has yet been confirmed, but each offers a thoughtful, careful vision of what lies beneath everything we see. Neither of these leading theories yet fully explains the universe's overall structure. They offer elegant ideas about the smallest imaginable scales, yet struggle to speak clearly about the shape and size of everything at once. Scientists continue refining both frameworks, patiently searching for the missing pieces that might connect the tiniest threads to the grandest cosmic patterns. It is careful, unhurried work, built one insight at a time. The question of whether the universe is finite or infinite may never be fully resolved. Some mysteries, it seems, sit gently beyond the reach of any telescope or equation we currently possess. This is not a failure of curiosity, but simply the nature of asking about something so vast it may extend beyond all possible observation. Scientists continue searching softly, aware that certainty may always remain just out of reach. For a little while now, simply let these vast questions rest beside you, unanswered and unhurried. There is nothing you need to solve tonight, nothing to hold on to. Let your breath grow slower, your shoulders sink a little deeper into the softness beneath you. Let your thoughts drift the way starlight drifts, unbothered by distance or destination. You are safe here, wrapped in stillness, needing only to rest. Some thinkers argue that the question of a finite or infinite universe is scientifically meaningful, yet practically unanswerable. It touches real physics, real geometry, real measurable curvature, yet the scale involved may forever exceed what any instrument could ever observe. In this view, the question deserves serious thought, even if a final answer never arrives. It is a question worth holding gently, rather than one that must be solved. Others argue that this question leans more toward philosophy than strict science. Since no experiment could ever confirm infinity itself, some scholars feel it belongs to the realm of reflection and reasoning rather than measurement. This does not diminish its importance. It simply places it in gentle company with humanity's oldest and most patient wonderings about existence, meaning, and scale. Philosopher Karl Popper argued that scientific claims must be falsifiable to belong within the boundaries of science. In his view, a genuine scientific idea must allow, at least in principle, for some observation that could prove it wrong. This simple standard shaped how generations of scientists tested and refined their theories. It offers a quiet lens through which to examine even our grandest cosmic questions. It claimed that the universe is infinite may be unfalsifiable in principle, since no observation could ever fully confirm or disprove something without end. We can only ever observe a finite portion of space, no matter how powerful our instruments become. This leaves infinity as an idea we may approach, but perhaps never verify. It remains a graceful, open possibility rather than a settled fact. A claim that the universe is finite, however, could in principle be tested through the detection of curvature. If space gently curves back upon itself, like the surface of a distant sphere, careful measurements might one day reveal it. This gives the finite hypothesis a quiet scientific foothold that the infinite hypothesis may lack. It remains a hopeful, measurable thread within an otherwise open question. Future telescopes may refine our measurements of cosmic curvature even further than we can manage today. With gentler instruments and steadier precision, scientists hope to narrow the smallest remaining uncertainties in the universe's shape. Each refinement brings us a little closer to understanding, even if perfect certainty stays gently out of reach. It is quiet, patient progress, built slowly across generations of careful looking. The James Webb Space Telescope now observes deeper into cosmic history than any instrument before it. Its mirrors, cooled and unfolded far beyond Earth, gather light so faint and so old that it has traveled since the universe's earliest chapters. Galaxies once invisible now emerge as soft smudges of ancient light. Each new image quietly extends how far back in time our eyes can gently reach. Future missions may search for subtler patterns within the cosmic microwave background, hinting at the universe's hidden topology. Scientists imagine instruments so sensitive they could detect faint echoes of shape folded into that ancient light. Such patterns, if they exist, might whisper whether space curves back upon itself far beyond our sight. For now, this remains a hopeful, patient search into something impossibly delicate. Improved precision could someday distinguish a perfectly flat universe from one that curves ever so slightly. The difference at stake is smaller than a whisper, hidden within measurements taken across billions of light-years. Instruments of the future may sharpen this distinction, narrowing uncertainty toward something closer to knowing. It is a slow tightening of focus, like adjusting a lens by the faintest careful turn. Even a perfectly flat measurement would not prove the universe is truly infinite. Flatness only describes the shape we can observe within our own cosmic horizon, not the nature of space beyond it. A vast, gently curved universe could still appear flat within any region small enough for us to measure. Certainty of infinity would always slip just beyond the reach of instruments. For a while, let your thoughts settle like dust after a long, slow breath. There is nothing to solve here, nothing to hold on to. Let your shoulders soften into whatever is supporting you. Let your breathing slow, unhurried, each exhale a little longer than the one before. You are allowed to simply rest. Absolute proof of an infinite universe may remain permanently beyond scientific reach. No telescope, however powerful, could ever survey a boundless expanse in its entirety. We may forever gather only fragments, however vast, of something that never truly ends. This is not a failure of science, but perhaps a gentle boundary built into the nature of asking. Some physicists argue that infinity is simply the most natural default cosmological assumption. To them, a universe without edges or boundaries requires no special explanation, no unusual construction. Finiteness in this view would demand an extra reason for space to stop somewhere. Infinity quietly might be the simplest starting place of all. Occam's razor might favor the simplest model that avoids invoking an artificial boundary. This old principle suggests that, between competing explanations, the one requiring the fewest assumptions is often the most graceful. A universe that simply continues, without an edge needing explanation, may satisfy that principle more naturally. Simplicity, in this quiet way, becomes its own kind of guide. Others argue that only finite quantities are ultimately physically meaningful. In this view, true infinities may belong only to mathematics, not to the physical world we inhabit. Nature, they suggest, always seems to resolve into countable, measurable amounts, however large. Infinity, then, might be a beautiful idea that reality itself never fully holds. This debate connects to deep, unresolved questions in the philosophy of science. It asks not simply what the universe is, but what kinds of questions science can ever hope to answer. Where does careful measurement end and quiet interpretation begin? These are old questions, wrapped gently around one of the newest mysteries we know. Perhaps someday, new mathematical frameworks will offer fresh ways to frame this question entirely. Mathematics has surprised us before, revealing hidden structures once thought impossible to imagine. Future tools, not yet dreamed of, might dissolve old dividing lines between finite and infinite into something more subtle and whole. The question itself may quietly evolve even before it finds its final answer. And so, tonight, the universe's true size remains one of cosmology's greatest open mysteries. Finite or infinite, it holds its answer quietly, just beyond our careful reach. Generations of patient minds have measured, calculated, and wondered, drawing closer without ever quite arriving. The mystery itself, vast and unhurried, simply continues to wait for us. Contemplating this possible infinity often gently humbles our human sense of scale. Beside such vastness, our daily concerns soften, feeling lighter rather than heavy. This is not a diminishing thought, but a freeing one, placing us tenderly within something immeasurably larger than ourselves. Humility here feels less like smallness and more like belonging. Whether finite or truly infinite, the observable universe alone already exceeds human comprehension. Its trillions of galaxies, its uncountable stars, its ancient traveling light form a vastness the mind can only touch in gentle fragments. We do not need the final answer to feel its scale. Wonder arrives long before understanding ever could. The search to determine the universe's true extent continues, quietly, to inspire wonder and careful inquiry, generation after generation. And perhaps that ongoing search is itself the gift, more than any final answer could ever be. Tonight, you have traveled across billions of light years, through ancient light and patient equations, resting always within the same vast, breathing universe that holds you now. Wherever it ends or does not end, you are here, small and cherished, held gently within it. Let your breathing slow, let your body soften into rest, and let the universe carry on its quiet, endless work while you sleep. Good night.